Hi! Today's lesson is about how we can divide the periodic table in a number of ways. Before we get started, let's please review two important vocabulary words that we learned last lesson. The first is that of period. Every time you hear the word period and associate it with the periodic table, you absolutely must understand that we mean the left to right direction, or a row on the periodic table. There are a total of 7, and we learned last lesson, that was indicative of the energy levels, or the rings, around the nucleus of an atom. The second vocabulary word we learned last lesson was that of group. It is absolutely imperative that when you hear the word group associated with the periodic table of the elements, you understand that its direction is the up and down. In other words, it's a column. Another synonym for a group or column on the periodic table is that of a family. And we talked about how Dmitri Mendeleev prioritized grouping these elements into these families so that they shared similar chemical and physical properties. If we are to count, there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 groups on the periodic table. And part of today's lesson is to learn about what information that can tell us about the structure of the atom. Just like the periods were indicative of the energy levels in an atom, the groups will allow us to have some insight into the inner workings of the structure of the atom as well. The first division of the periodic table lecture we concluded in our last lesson, how the structure of the atom and the location of the electrons is one way that we can organize or divide up the periodic table into our S block elements, the P block elements, the D block elements, and the F block elements. We watched a video last class that introduced us to some special names, and that's going to be where we begin today. The elements in group 1, but not hydrogen, these are the alkali metals. Alkali, A-L-K-A-L-I, metals, alkali metals. And if we think back to our homework from the other night, all of these elements had the S1. Maybe it was 1S1 or 3S1 or 4S1, but they all had S1 as their valence shell electron configuration. To the right of the alkali metals are the alkaline earth metals. Alkaline, A-L-K-A-L-I-N-E, alkaline earth metals. If we think back to our homework from the other night, their valence shell electron configuration ended s2. Again, maybe it was 1s2 or 6s2, but they all ended s2. The next group we're going to talk about is again to the right of the alkaline earth metals. And it encompasses all of the elements in our D block. These are referred to as the transition metals. Transition metals. I will go over this again in a darker colored ink. My apologies. Transition metals. If you think back to our electron configurations, there wasn't anything consistent per se moving from left to right. There were consistencies in the up and downs, but ultimately these are our D block elements. Before we proceed, let's talk about a couple things. In the video last class, we learned that the alkali metals and the alkaline earth metals are very reactive with water. I'm going to put with water in parentheses because ultimately they're very reactive, period. In other words, they are so reactive that you will not find them as elements in nature. You will not find them as elements in nature. The only way you can find sodium is locked up in a compound like sodium chloride. The only way you could find calcium is locked up in a compound such as calcium oxide. You saw, though, in the video that the scientists were doing experiments with the actual elements. How do they get them then? Well, they have to undo the compound. So they have to reverse the chemical reactions to pull out or extract the metallic element that they're looking for. And as you saw in the videos, you could possibly imagine that if these elements really did exist as elements in nature, every time it rained, we would have this production of hydrogen gas and these massive explosions. Some people would think that's a cool world to live in. I don't know. A cool thing about the transition metals is that they're going to give us colors. Or pigments. So for those of you who like to paint, the colors of the paint come from the presence of various transition metals in your paint. We also saw in our last unit how, excuse me, many of these metals can be used to give us the different colors in fireworks. So transition metals are well known for giving us colors or pigments in our everyday world. The next special name that we're going to talk about is over here with the elements in group 17. The elements in group 17 have a special name. They're called the halogens. Halogens. H-A-L-O-G-E-N-S. And if you think back to what their electron configurations looked like, they were always S2 P5. Let's work backwards for a second. If I look at the elements in group 16, their box said S2, P4. If I look at the elements in group 15, theirs said S2, P3. If I looked at the elements in group 14, their valence shell said S2, P2. And the elements in group 13 said S2, P1. If you look carefully at these groups, 13, 14, 15, 16, and 17, if you add up the total number of valence electrons, it will be equal to the number in the ones position for the group that they're in. So just a few minutes ago, I told you that we would learn how the group that an element is placed in can give you some insight into the structure of the atom. The pattern that we're developing is that when you're in group 1, there's 1 valence electron. When you're in group 2, you'll have 2 valence electrons. Skipping the transition metals, when you're in group 3, you'll have 3 valence electrons. When you're in group 14, you'll have 4 valence electrons. Group 15 will have 5 valence electrons. Group 16 will have 6 valence electrons. And elements in group 17 will have 7 valence electrons. That brings us to the elements in group 18. These elements, again, have a special name. The reason why we skipped elements in the groups 13, 14, 15, and 16 is because they don't have a special name. They're just called the boron group, the carbon group, the nitrogen group, the oxygen group, etc. Kind of boring. The elements in group 18 are called the noble gases. Noble gases. And when we look at their electron configurations, the helium box said S2, but all of the other ones said S2, P6. If we follow the pattern that we established just a moment ago, adding up the numbers 2 and 6, so the total number of valence electrons, equals 8, which is the number in the ones column of the group that it's positioned in. So we have that relationship. And this now starts our conversation of why helium is positioned here in group 18 and not over here in group 2. And that's because the noble gases have what's referred to as a full valence shell. And as we heard in the video last lesson, this is what all atoms strive to have. All atoms strive to have this electron configuration. So whether we're carbon in group 14 or oxygen in group 16, that atom wants or strives to be stable, and being stable is having a full valence shell. This is considered stable. It's a low energy state for nature. So what can we do with this knowledge now? We can now finally learn the last way to write electron configurations, and that is called the noble gas electron configuration notation. Noble gas electron configuration notation. Let's say, for example, I wanted to organize oxygen. Oxygen would be 1s2, 2s2, 2p, 4. Noble gas electron configuration implies that somewhere hidden in there is the electron configuration for a noble gas. Well, looking at my noble gases, helium is 1s2. This part here comes from helium. So if I put helium in brackets and then follow it up with the remainder of what the electron configuration looks like for oxygen, that's another way to write oxygen's electron configuration. Let's do the example for chlorine. Chlorine has 17 electrons. 1s2, 2s2, 2p6, 3s2, 3p5. Well, when I get to this combination here, right, this one, 1s2, we said is helium. This 2s2, 2p6 is going to be neon. And then my next noble gas doesn't come until I hit 3p6. So the way that I would write chlorine's noble gas electron configuration is I'd put neon's symbol in brackets. And that's telling the reader, organize all of the electrons for neon. And then continue from there. 3s2, 3p5. We'll do one more example. We'll do copper. 1s2, 2s2, there are 29 electrons, by the way. 2p6, 3s2, 3p6, 4s2, 3d9 is what you want to write, but this is an exception. We take 1 from the s and we put it into the d. Writing this as electron configuration noble gas style, well, the 1s is helium, the 2s2p is neon, the 3s2 3p6, that's going to be argon. And then I haven't gotten to organizing enough electrons for krypton yet, so I haven't made it there. So I put argon's symbol in the brackets, and that's telling the reader, organize all of argon's 18 electrons, and then the rest go into 4s1, 3d10. So now that you know where the noble gases are found on the periodic table, you can write the noble gas electron configuration notation for any element on the periodic table. In terms of divisions, we've got 2 more to go. The next special name is going to be given to the 4F group here. These are our lanthanides. Lanthanides. And beneath the lanthanides are the actinides. Actinides. Here's where we have a lot of our radioactive elements. Radioactive elements. A small number of them are found in nature. Most of them, though, are man-made. So we've now learned another way to divide the periodic table, and these are called the special names. We can divide them into the special names. Our first division, remember, were our electron configurations. And this second way to divide them are with the special names. There are a couple more ways we can divide the periodic table. The next will be based on where we find metals, nonmetals, and metalloids. Metals, nonmetals, and metalloids. In order for us to make the division, we need a boundary, and that boundary is going to start with boron. Let me choose a different color and perhaps a little thicker. I am now going to be making a bolded staircase where I go down 1 over 1 incrementally on the periodic table. So again, we started at the bottom of boron's box, and then we go down 1 over 1, down 1 over 1, down 1 over 1, and so on. And that's going to be our boundary between metals and nonmetals. Metals, when you hear that word, I hope you think nickel, copper, silver, gold, mercury. Now maybe you're adding sodium, potassium, calcium to that list. Those elements are found to the left of the staircase. Generally speaking, our metals will be found to the left of that staircase. The nonmetals will be found to the right of the staircase. That's where we'll find our gases. Except for hydrogen. Despite the fact that hydrogen is positioned to the left of the staircase where the rest of the metals are, hydrogen is a gas. It is considered to be a nonmetal. Metalloids, those are elements that have properties of both metals and nonmetals. They're the ones that are going to exist on the staircase. So boron is an example of a metalloid. Notice that I've skipped over aluminum. Despite the fact that aluminum is on the staircase, it is not considered to be a metalloid. All right, so my little key here is the purple squares are the metalloids. Let me switch back to my navy blue. My metals are going to be including that aluminum one. These are all my metals. And the lanthanides and actinides, because remember, they're positioned in here. They're to the left of the staircase. Those will be my metals. And then the nonmetals, oh, my color coding was off. Let me change hydrogen's box to a red. Sorry about that. Nonmetals will be red. So that's yet another way to divide our periodic table. The final way that we will divide up our periodic table is based upon states of matter. Yes, we know that 4 states of matter exist. For our purposes, though, we only work with the big 3: solid, liquid, and gas. There are only 2 elements whose state of matter at room temperature, because as we know, if we can change, like if you increase or decrease the temperature, you can pass through the various states of matter. So when we're describing this organization or division of the periodic table, we are keeping the temperature constant, which is room temperature. There are two liquids on the periodic table: mercury, whose symbol is Hg, and bromine, whose symbol is Br. The next division we'll talk about are the gases. There are 11 elements on our periodic table that are gases. They're the noble gases, easy to remember thanks to the name of their special group here. So we've got all of our noble gases here. That's 1, 2, 3, 4, 5, 6, well, 7. This is our newest discovery. It's not counted in the 11, sorry, so I'm just going to count those 6. Then we've got oxygen and nitrogen. Then we've got fluorine and chlorine. Hydrogen. And I believe that's it. 1, 2, 3, 4, 5, and 6 is 11. Yep. And there's our other gas. And everything else is a solid. Everything else. So dividing up the periodic table by states of matter isn't really by where the elements are positioned. It's more of just flat out memorizing. There are 2 liquids, mercury and bromine. There are 11 gases, and the gases are sort of clumped together in the sense, again, like we said, we're the noble gases, and then you've got these 4 here, plus hydrogen. So the gases tend to be clustered together, and then everything else is going to be a solid.